All right, everybody. So this is our next section of our Unit 10 notes, and we are looking at the effects of changing dimensions for 10.2 and 10.3 three-dimensional figures. Okay, so we first start off with this think, pair, share. So you're just talking about what you think the definition of a polyhedron is, and actually it's quite simple for us. What we're going to say is a polyhedron. Oops, it did not. Yep. Polyhedron is a three-dimensional solid with, we're going to say flat surfaces, and we're going to say straight edges, just like that. Yeah, that's how we'll define it for right now. There is a more proper definition, but that's going to be a little later. And although we start with learning this item called a polyhedra and some items that are not called polyhedrons, we're going to first go back a little bit to more area stuff first, and go ahead and take these notes down. Okay, these notes are important for us to decipher the differences between heights at top, just like this. Okay, I think a lot of us already read it like this, but just so we're all very clear on it. Okay, so we're going to do this in a couple of ways. And so what we're trying to do here first, we're trying to describe the change that happens with the perimeter in the area of each figure. Well, whenever we look at the first figure, we can obviously see this is a triangle, and anything with perimeter is just adding all the edges on the side. So we're going to start with perimeter. E is going to equal 3 plus 4. In case we don't already know, this is a Pythagorean triple. We know this because, well, it's a right triangle. It's got 3 and 4 as the legs. Therefore, our third side, our hypotenuse must be the 5 here. And that's just going to give us our 12 inches. Sorry, 12 centimeters. Pretty simple. We'll find our area. And our area here is going to be our 1/2 times the base 3 times the height 4. That's going to give us our 6 centimeters squared. Okay, pretty simple. But however, if we double this height, right, if we make our height twice as long, we're going to see a little bit of a difference. Okay, so I'm going to draw a new triangle over here so we can see the difference. We're still going to have this 3 for our base because the base isn't changing, only the height's going to change. So we're going to have that 8 centimeters here, 3 centimeters here. And because we have a new change here, we have to make sure we find that third side again because it's not going to be 5 anymore. Okay. So you can use Pythagorean theorem to find that other side. I've already done it for you, of course, or I've already done it on my paper, so I'm going to just kind of put that in here. So we get perimeter equals 3 plus 8 plus the square root of 73. Okay. So now that we found that, we're going to add them up. We round off our answer to 3 decimal places. We're going to get 19.544 centimeters. Then our area, we'll still have that 1/2. That's for every triangle. Our 3 base never changed, but our height changed to an 8. And this is now 12 centimeters squared. And now something that we should be asking ourselves is what happens between the two different changes? We have an original in red, and then now we have a different one in blue. So why do we go from red to blue? Of course, we could just say that we doubled the height, right? We just multiplied by 2. But is there any relationship between the perimeter and the area? Well, the way to think about it, or at least the way I think about it, is if we go from one perimeter to the other perimeter, we start off with a very nice number, 12, right? Very nice, respectable number. But then you go into the other perimeter, and the other perimeter essentially goes on for infinity, right? Remember that the 73 here is not a perfect square. And so because it's not a perfect square, it's going to go on for infinitely long. Okay, that's just kind of the way of the world right here. Okay, so this is going to go on infinitely long, no matter how much it's going to go. And yeah, you're essentially going from 12 to, in a way, infinity, but not quite in the infinity that we think. Okay. However, there is a direct link between the areas, and the area did double in size. Okay, so if you took the notes at the very top here, where it says one dimension, that's essentially what's happening here. Anytime we increase or decrease the dimension by multiplication, then what happens here is, well, whatever multiplication happened is going to happen to the area. Okay, so if we started out at 6, we multiplied the height by 2, we see the new area is 12. Well, we multiplied by 2. That's how we know that for sure. Okay, and we'll do the same thing over here on the other side, just to show that it does work for rectangles as well. So we'll start off with our perimeter. Now remember, perimeter is all the edges added up together. And since I have a rectangle here, which means opposite sides are equal to each other, 2 times 12 plus 2 times 5 is going to give me the value that I'm looking for. I get 24 plus 10. It's going to give me 34 feet. Area for us is very easy. We're just looking for the length times the width. So we're going to have 5 is 12, and that's going to equal 60 feet squared. Okay, all should be pretty darn easy. We'll keep going. This time we want to multiply the length by a third. Well, remember, right, we have to be specific with ourselves of which one is the length, which one's the width, and this bottom 12 value is going to be our length. So good draw. We're going to say this is now a 4, this is a 5. Of course, my drawing is not up to scale. That's okay. Don't worry about it. But we'll do the same exact approach. 2 times 5 is 2 times 4 equals 18 feet. Area is going to be that 4 times 5. That's going to give me 20 feet squared. Okay. And so, like I said in the last problem, we're not actually seeing any real correlation between the first perimeter and the second perimeter, at least not anything that we can really make sense of. So we're just going to leave that as bygone thought. However, we do see that the area did change again by the factor of whatever is being multiplied. So since we are multiplying by 1/3, our area shrunk to only 1/3 of the original area. So just make sure that you're aware of that. Okay. And you know, one thing that I want us to be really sure of and point out for us here is that this is what we call an unproportional changing of dimensions. Okay, non-proportional just means all, or I should say not all dimensions change at the same rate. This is essentially what that means. Okay, so I wouldn't worry too much about it. I don't really think we're going to be doing any non-proportional transformations. It's just not really something that we're going to do. Probably other things, but not non-proportional. Okay. Well, this is just a single dimension that's being multiplied, but we can possibly have multiple. In this case, we do have multiple. Okay. And just to save us some time and to, you know, save us some effort, we're not going to look at the perimeter. We will, however, look at the area. Okay. And something I didn't do in the last problem is that I didn't specify some of these words here. Okay. So doubling just means to multiply times 2, much like how tripling just means to multiply times 3. Okay. So doubling, tripling, those are very common words that you could use. I mean, obviously in real life speech, but also in our mathematical speech. So make sure that you know what doubling and tripling means as far as a mathematical sense, although they're the same sense, essentially. Okay, we'll find our original area. This is going to be some sort of rectangle. We know for sure because all 90-degree angles here. 6 times 7 is going to be our width times our length. So just specifying exactly right. So our 6 is going to be our width or 7 is going to be the length. Okay, you have to specify that. And we get 42 feet squared. However, if I'm going to change it, I'm going to double my length. So I'm going to make a new rectangle. I'm going to double my length, which is going to be 14 meters now. And I'm tripling my width. Well, so 6 times 3 is going to be 18 feet. And so theoretically, what's going to happen is that we're going to multiply these two. 18 times 14. We're going to get some value. This is actually going to be 252 feet squared. And these two values, or rather, this 252, you can get that value from multiplying the two factors that were multiplied each other. So what I'm referencing is actually up here. Okay. If I have the width being multiplied by a j, let's just call this j 3, right? So 3 equals j. Then I have this other value 2, and that's multiplying the length, we'll call it k. Then in theory, we should get jk, oops, which is going to be 2 times 3. And that's going to equal 6. Well, if I take 252 and divide it by 6, I get 42. Okay, and actually, this is the day after Jackie Robinson Day, so number 42, if you're a baseball fan out there. But yeah, so we have this idea with us here. Okay, so make sure that you understand that we can actually make things a little bit easier for us. So instead of having to make a new shape, instead of having to do all this other stuff, we can just make things a little bit easier on ourselves. Okay, so we're going to take what we learned here and apply it to the second problem. We'll first start off by finding the area first. So the area of any triangle is going to be 1/2 times its base, which is 6, times the height, which is 8. And we actually are going to get a value of 24 inches squared. Okay, that's A, our area. But now let's look at what it tells us for our change. We have a 1/2 and we have a doubling. Okay, so double again means times 2. But if I multiply my base, call it, or multiply my base with a 1/2, we'll call it j. Then we have a doubling, so 2 times, call it k. If we get jk, we get 1/2 times 2, and that would just simplify to 1. And now some of us will be like, well, that doesn't make sense. And it actually kind of does make sense. What this is essentially telling us is that the area doesn't actually change. The perimeter might change, but the area will not change. Okay, so this area for the new triangle will be 24 inches squared, and we can definitely confirm that if we wanted to. So we'll change our height to be double what it is, so 16. We'll change our base to be half of what it is, so we'll change it to 3. And so we get this area equal 1/2 of 16 times 3. And that does in fact give us our 24 inches squared. Okay. So we made things a little bit easier for ourselves, and that's always a good thing. Okay. Now, this is the only set of notes that you really need to take for this slide. It just basically helps us do things a little bit better, assuming that there is proportionality. Okay, so otherwise this will not work. So if you are not changing dimensions proportionally, meaning the exact same value, then you cannot just do this. Okay, so make sure that you are doing what you got to do correctly. Okay. Now, as far as these shapes, we're actually not going to find the area or the perimeter. However, what we are going to do is we're going to figure out what happens whenever we change these. Okay, so we'll first describe the perimeter. We'll first find this perimeter here. We'll describe this new perimeter as new P. Okay, nu p is our perimeter. So if we have this perimeter here, we're going to take the original perimeter p and multiply by whatever the actual value we're multiplying by. So since we're saying doubling, we're going to say times 2. Our k value is now 2. So 2 times p. And what does that really mean in words? Perimeter gets doubled. And that's it. Just to give us a little reminder, that does mean times 2. And that's essentially it for our perimeter. However, for our area, it's going to be a little bit different. And we're going to say our new A. We know we're going to keep our A on the side here. And if we're multiplying proportionally, we go back to the diagram here, it actually tells us that we have a k squared. So if our k was 2 here, you need to make sure that it's going to be squared this time. And of course, 2 squared is going to equal 4. 4 times A is now 4A. And what this means now is that the area gets quadrupled. Okay. Now, for a lot of us, we probably aren't going to say quadrupled a whole lot, but I would say double, triple, and quadruple are very common in the mathematical world as far as the shorthands to say multiply by 4, multiply by 3, multiply by 2, and whatnot. Okay, anything above quadruple is kind of uncommon. I would say probably the least amount of common between any of them. So I wouldn't be too worried about it per se, but I would definitely make sure that instead of saying times 2, just say doubled. It's just going to be easier. Now go ahead and try extra example 3. And once you come on back, we can just get in our answer right here. We know we're quadrupling, so we just talked about that equals times 4. So if we're looking for a perimeter, 4 times p, and it's pretty simple for us to figure it out. Perimeter is quadruple. There's an L right there. Right there. Okay. And of course, it's times 4. However, my area is going to be a little bit differently. I'm going to have 4 squared times A, the area, and that's going to equal 16A. Well, like I said beforehand, anything above 4 is kind of just a whatever. We're just going to say the area is multiplied. Just either by, oops, we don't need all that, 16. And then our in our parentheses, we're going to make sure we notes 16. Okay, so there we go. These are the next set of notes. You can pause the video and get these in. A lot of these terms you already know, so we already know what an edge is, we know what a vertex is. Maybe we haven't heard face a whole lot. Polyhedrons we introduced at the very beginning, and we now know how to say it plurally, polyhedra or polyhedrons. And we want to make sure that we identify the base, okay? Identify the base. It's from what I can usually say, it's usually going to be the one that is most unique. Okay, so if we look at the right-hand side here, we have a pentagonal prism. And we're going to call it a pentagonal prism because, well, it's a pentagon, right? And all the other shapes are going to be rectangles. And we're just going to call it by whatever uniqueness we see. And so if a pentagon is the unique figure we see, oh, excuse me, pentagon is the unique figure that we see here, we're going to call it a pentagon. Okay. Now, as far as the pyramid down here, pyramid's going to be a little bit tricky with a triangular pyramid because it might be hard to tell which one is going to be your base. However, there's usually a way to tell the base because usually it's going to stand upright and not be on its side. Usually, but in the event that it isn't, I would say probably the one that is, again, unique from the other 4, or from the other three, because there's only 4 triangles on a triangular pyramid, I would say probably the one that's not uniform with the rest of them. It's probably going to be your base. I don't think it's an exact science, but that's just what I'm thinking off my head right now. Okay. And so here we're just going to classify, and I already have all the answers here, right? All of them are right here. But the check marks mean that this is a polyhedra, and then the not check marks means that it is not a polyhedra. Okay, so just kind of making sure that we can tell which ones are and are not polyhedrons. And then being able to name what these are. Okay, so again, you identify them by its base. So if the base is a rectangle and there's no other unique shape, you're going to call it a rectangle. Rectangular prism, I should say. And then we see the hexagonal pyramid and the pentagonal pyramid and whatnot. I think those are easy enough to figure out. Okay. Remember the kind of main difference between the pyramid and the prism is that the pyramid has like a central like vertex, if that makes sense. It has like one really like pointy part of it that multiple faces go towards it. However, the prism for sure can have some points in it. However, not nearly as, I guess, defined and definitive as the pyramid does. So just kind of keep that in mind. And for this half sphere, right, we're going to call that a semisphere or a hemisphere. I personally prefer hemisphere, but that is entirely a preference afforded to you. Okay, so I wouldn't feel too bad about it. Next, we have what's called a cross section. And I want to be very clear that we are not looking at what the plane is. We're looking at what the plane and the solid are creating as their intersection. So this one says square, right? We know this is a cube, so yeah, all of it is made of squares. But we're looking at this purple square right there. And that's what we're saying is the cross section. Similarly, we see a rectangle on this middle one, and in the purple here, it definitely looks like a rectangle. And same thing with our triangle here. This definitely looks like some sort of triangle. Okay, so make sure that you know what problem you're looking at and whatnot. Okay. And with these ones, I also have all the answers, right? We have hexagon, triangle, rectangle, circle, trapezoid. Maybe I jumped the gun a little bit. Maybe you should have tried it on your own first. Similarly with the other parts, try it on your own first, see if you can get them right. Otherwise, you already have the answers here. Okay. Nothing too difficult, I don't think. Although part C is definitely an interesting piece to this, only because you wouldn't normally see a rectangle in a cylinder, at least not immediately. Okay, so cylinder is going to be interesting. And actually, we're going to talk about cylinder in the next slide. And this is what we call the axis of revolution, or rather the solids of revolution. Okay, but we have that axis of revolution here. And so essentially to kind of get, if you're at your house listening to this, or if you're close to some sort of paper towel or bathroom or such with toilet paper, just, take a piece off and really like look at what it actually is. Is it a rectangle? Is it a square? All that stuff. But it's all wrapped around this basically a roll, right? That's a cylinder. And that's essentially what we're working with, right? We have some sort of rectangle that's going around some sort of axis, and it creates our cylinder. Okay, so kind of the same idea as like if you were to split a soda can in half, like and just like stretch it all out, it looks like a rectangle. Okay, it all looks the same. It all looks interesting. But it gives us actually a couple of bits of useful information. So if we start off here, right, we're looking at this rectangle and we're told to sketch the solid produced from rotating on the given axle. Well, we just talked about how a rectangle would turn into a cylinder, so just draw a cylinder. That one's pretty easy. So we'll draw a circle. Now this is the part where it gets a little tricky for some of us, right? We're actually not going to draw another circle. We're going to draw 2 lines like this. We're going to create like a half circle here, and then a dotted half circle over here. Okay, we'll just pretend that's all dotted up. Okay. Now I realize and I recognize that the illusion of 3 dimensions does look weird. It does. We can all say that. However, my suggestion to you is anytime you see a solid line, imagine that as the front, the forefront, exactly what you see in front of you. And anything that's dotted, think about it as if it's behind the shape. Okay, it's still part of the solid, but it's behind the back or the front images and whatnot. Okay. Well, this is a lot of good information here. We have this 4, we have this 9. Okay. Obviously, we're saying that this 9 kind of rolled, right? It kind of rolled with the paper towel, if you want to guess, I guess if you want to call it, right? And that's actually what we're going to treat as our height. So 9 is going to be our height here. But if I have this axis of revolution with this 4, the 4 is the part that's going to be wrapped around as well. 4 is going to be our radius. Okay, so a couple key things that we need to see from this. Obviously, it's a cylinder, so we'll kind of write that in, cylinder. We know it's not polyhedron. And we know we have a circular base. Okay, just some nice things to know. But it's not just limited to our rectangles. We can also have it for our triangles. And obviously you can make your own guesses as to what this is going to be. I think it's pretty obvious for some of us, but we're actually going to make a cone. And the cone is actually quite easy to make. I think this is probably one of the easier ways to make it. In the event that you do want to make this like back half here, a dotted, that's perfectly acceptable. It kind of just works on preference as what you need to. Okay. So this will work pretty much the same way. We know that we have some value 2 here. It's 2 is going to be our radius. And then we have a value of 5. That's going to be our height. Okay, so we'll have that. Of course, we're working with a cone. It's not polyhedron. And then, of course, we have a circular base. Okay, all the nice things. Go ahead and try the extra example 6. Just kind of good practice. And it doesn't really matter necessarily how you draw it as far as the orientation goes. You can draw it upright, facing downward, side to side. It doesn't really matter all that much. I usually try to figure out and draw it the way it's supposed to, how it's oriented to me when it's given to me. That's why I drew the previous 2 pictures the way they did, right? The cylinder side to side and the cone base down, pointing end up. But it's really just a preference thing. But I do prefer drawing it in the way that it shows me first. So my cone looks like this. I'm going to, or my triangle looks like this. I'm going to draw it somewhat similar to that. But pretty much the same thing. We have a 5 for our radius, and then we have an 8 for our height. Okay, and it's a cone. It's going to have the exact same properties as the other cone. Okay. Well, that was that was 2 lessons that we covered here today. I mean, really the classifying of the 3D objects started here, right? So a little bit under halfway, I would think, maybe a little over halfway. I'm not really sure, but we're pretty much done right here. And that is it for 10.2 and 10.3. As always, if you have any questions, feel free to ask in class at an appropriate time or after school and such at tutorials. But for right now, I'll let y'all go and you have a great day. Bye-bye.